Welcome to a journey into the mind of a master architect of the molecular world. This slide introduces The Blueprints of Nature, an exploration into the scientific art and intellectual legacy of Robert Burns Woodward. Regarded as one of the greatest organic chemists of the 20th century, Woodward transformed the field through the synthesis of complex natural products. The imagery contrasts the rigid geometric lines of an engineering blueprint with the intricate, organic complexity of a molecular model in his hands. It sets the stage for a story about creativity, precision, and how one man decoded nature's most sophisticated designs to reshape medicine and chemistry forever. At the heart of Robert Burns Woodward's revolutionary approach lies the Woodward Triad, a framework that elevated organic chemistry from trial and error to a predictable, elegant art. This Venn diagram illustrates three intersecting pillars: instrumental analysis, which pioneered UV, IR, and NMR spectroscopy to rapidly determine structures instead of using tedious wet chemistry; rational design, which treated organic synthesis as a predictable science guided by physical organic principles; and aesthetic elegance, which approached molecule building as a strategic art form prioritizing symmetry and concise logic. Where these three principles converge, we find the true essence of the Woodwardian era, masterclass in transforming complex synthesis into a beautifully engineered, predictable, and elegant science. Every master architect has a foundation, and Robert Burns Woodward's origins reveal a prodigy in the making. This timeline highlights his early obsession with chemistry. In 1925, at just 8 years old, he mastered Ludwig Gattermann's classic laboratory manual in his Quincy, Massachusetts, basement. By age 11, he wrote to the German consul general to obtain copies of Liebig's aniline, discovering the Diels-Alder reaction. His unconventional brilliance peaked between 1933 and 1937. Enrolling at MIT at 16, he was expelled for skipping classes to live in the lab, only to be readmitted, earning his PhD by age 20. This extraordinary journey forged his lifelong belief that intense thought and encyclopedic knowledge could solve any complex problem. To truly understand Robert Burns Woodward's influence, we must examine the paradigm shift he initiated in chemistry. This comparative matrix highlights the transition from the trial and error wet chemistry of the era before 1940 to the innovative Woodwardian era. Woodward replaced slow, laborious methods with rapid, accurate spectroscopic techniques using UV, IR, and NMR. Stereochemistry, once often ignored or left to chance, was now deliberately engineered and strictly controlled. This shift transformed organic chemistry from a manual, technical craft into an elegant, intellectual art, profoundly redefining how scientists engage with molecular structures. Quinine, the first masterpiece, marks a pivotal moment in chemistry, showcasing that complex natural molecules can be synthesized through scientific innovation. In 1944, the Allies faced a crisis when they lost access to natural quinine supplies from Java. In response, Woodward collaborated with William von Eggersdorff to develop a formal total synthesis of quinotoxin, a precursor that converts to quinine. Although the process was too expensive for wartime mass production, its scientific importance was immense. It proved that constructing complex natural molecules was possible through pure reasoning and careful planning, transforming the field of chemical synthesis. This slide, titled The Problem Solver's Blueprint, illustrates Robert Burns Woodward's legendary ability to bypass years of manual lab work through pure, structured thought. The diagram maps his cognitive journey, transforming a chaotic tangle of misleading, contradictory experimental data into a perfectly resolved terramycin structure. A famous quote by Nobel laureate Derek Barton captures the feat, noting that Woodward took a large piece of cardboard, wrote down all the facts, and by thought alone, deduced the antibiotic's correct structure, a breakthrough nobody else could have achieved at the time. Woodward's problem-solving involved systematic analysis, logical deduction, and visualization techniques that students can emulate to approach complex chemical problems more effectively. The key concept here is revolutionary. Woodward proved that the most daunting problems in chemistry could be solved entirely by intense intellectual analysis. This slide, titled The Staircase of Complexity, highlights Woodward's remarkable achievements in total synthesis, inspiring confidence in the power of scientific perseverance and innovation. Step 1, 1951. He synthesized cortisone and cholesterol, transforming flat, simple precursors into complex, 4-ring steroids. Step 2, 1954. He conquered strychnine, a 7-ring behemoth with 5 asymmetric centers, by leveraging the molecule's own rigid structure to thermodynamic advantage, showcasing his mastery over complex challenges. Step 3, 1956. Reserpine became a stereochemical masterpiece, in which he corrected a chiral error mid-synthesis by forcing the molecule into an unfavorable conformation to flip it. Step 4, 1960. Building chlorophyll involved the highest risk, as he constructed a densely packed porphyrin ring to create a natural driving force that facilitated the isomerization into the final green pigment, demonstrating his willingness to take bold steps in synthesis. We now reach the absolute pinnacle of 20th century organic chemistry, the B12 mountain. This slide underscores the complexity and scale of this synthesis, a feat that demonstrates the remarkable capabilities of scientific research. The sheer magnitude of this project is staggering. It required 11 years of relentless laboratory effort before its publication in 1973 and spanned almost 100 distinct synthetic steps. To conquer this mountain, a massive workforce of over 100 postdoctoral researchers contributed across a decade. This historic achievement was forged through a powerful transatlantic alliance. Woodward's Harvard team meticulously engineered the western half of the molecule, while Albert Esken-Moser's team at ETH Zurich constructed the eastern half, redefining collaboration in modern science. Scaling the B12 mountain unexpectedly exposed a profound gap in chemical knowledge, the theoretical anomaly. During the vitamin B12 synthesis, a specific ring-closing reaction consistently yielded stereochemical outcomes that completely defied classical chemical explanations. Woodward's brilliant intuition led him to realize that something deeper was at play. The reaction was being dictated by electronic and orbital symmetry, rather than just physical shape or basic thermodynamics. Recognizing the limits of purely empirical observation, he sought out a brilliant 26-year-old theoretical chemist to provide the mathematical and quantum mechanical rigor needed to back up his intuition. This breakthrough marked a significant milestone in the history of organic chemistry, highlighting the importance of integrating theory and experiment. This diagram reveals the elegant mechanics behind the Woodward-Hoffmann rules, the orbital symmetry diagram. Here, the mystery of the theoretical anomaly is solved. The rules dictate that pericyclic chemical reactions are allowed only when the symmetry of the electron orbitals is conserved from reactant to product. This conservation is rooted in quantum mechanics, where the symmetry properties of molecular orbitals determine whether a reaction pathway is energetically favorable. Published in a seminal 1969 paper in Adjuvant Chemie, this profound insight bridged the gap between highly abstract quantum mechanics and practical, benchtop organic chemistry, providing scientists with a predictive blueprint for seeing exactly how molecules would behave before ever stepping into the laboratory. We conclude our journey with The Conservation of Genius, a tribute to Woodward's enduring legacy that highlights his unique ability to bridge physical and theoretical chemistry. This architectural bridge illustrates how his work spanned two seemingly distinct worlds. On the left pillar stands the physical architect, representing the grueling 11-year physical labor required to construct the complex structure of vitamin B12. On the right stands the theoretical physicist, representing the mathematical and quantum mechanical rules of orbital symmetry that this monumental effort directly gave rise to. Woodward's true genius lay not merely in creating molecules, but in uncovering the underlying logic of nature that dictates how they are made. In his world, the artist and the theoretician were the same, forever changing the landscape of modern chemistry. This slide, titled The Persona and the Institution, explores the fascinating mystique and demanding culture that surrounded Robert Burns Woodward. His obsession with Woodward blue, wearing light blue suits, and driving a blue car reflected his unique personality, inspiring admiration and curiosity among students and readers interested in scientific figures. Professionally, he was an institution unto himself, known for his legendary mega-lectures. Impromptu, 4-hour sessions where he drew flawless, intricate chemical structures in multicolored chalk while chain-smoking. He also hosted the grueling Thursday night seminars at Harvard. Students and guests would struggle for hours to solve complex literary problems until Woodward stepped in after midnight to deliver the perfect, logical solution, cementing his status as a master mentor. We close with a reflection on Robert Burns Woodward's lasting influence. His 1965 Nobel Prize in Chemistry recognizes his groundbreaking achievements in organic synthesis, inspiring respect and admiration. Woodward's example demonstrated the deep fulfillment that comes from dedication to science, encouraging the audience to appreciate the value of perseverance. He passed away in 1979 at age 62, actively working on the synthesis of erythromycin until his final days. A peer's quote captures his impact, showing how he approached scientific challenges with confidence that intelligence and effort would succeed. His methodologies, predictive rules, and hundreds of disciples transformed organic chemistry into a rational, predictive art, leaving a legacy that continues to inspire.